Welcome to this video course on Python for geospatial big data analysis and big data science using the FASRC Harvard's High Performance Computing Cluster. My name is Robert Spang. I'm a visiting researcher here at the Center for Geographic Analysis at Harvard, and I'm originally from the Technical University of Berlin. I have the honor to spend the summer of 2023 here at Harvard. And one of my tasks that I really wanted to go into is how to leverage the high performance capabilities of the cluster here at Harvard for big data geoanalysis problems. Now, this course, of course, focuses on geospatial analysis using the FASRC, but I believe everyone who does some data science with Python will find some bits and pieces in this material that I prepared for you. And this course basically comes with 4 content modules. And each of these modules have a little bit of an input session from me to you, where I explain some concepts or some structures, show a little bit of how something is intended to work. And then we have a practical application of how we actually use that and apply that. And for this purpose, we have a case study prepared where you are encouraged to really work on a data science project where we combine different big data sets, and big as in it's not fun to use that on your computer locally. But we show you the strategies of how that can work and how you really tackle such a problem with your local machine on a little small example that you can then transfer to the cluster and scale it up so there the cluster works then on the entire data set. This course is not only done by me, but also by Devika Jain and Xiaokong Fu. Both are members of the Center for Geographic Analysis. And if you have any questions, if you want to discuss something, if that sparks some interest and you're curious about something, please feel welcome to get in touch with all of us. In the end of this workshop here in the outro, I have an overview of how to reach us and where our office is and where you can get in touch with us, because we very much encourage everyone who is interested in these kind of analysis and data science to really get your hands dirty, do it yourself, try it yourself, and also be in touch with us and others to generate knowledge and get better at this and understand things, challenge us, challenge our material. So the more you engage with what we prepared for you here, the better. These 4 modules, the introduction, the case study, how to apply all of that, what we have done until then, to the FASRC, and how to really optimize the performance so you can leverage the cluster attributes in terms of memory, CPU cores, and different details of or particularities of the cluster. These modules all come with this exercise later, and we try a little bit to keep it in a ratio of 1/3 of introduction and then 2/3 of really do it yourself. However, all of these exercises come with a solution. So in the GitHub repository that accompanies this course, you will find all the material that you need, but also the solution to the exercises. So if you're stuck, or if you feel like, well, I right now don't want to do this for hours, but maybe just get the gist of it, then you have the data and the scripts that we use in these exercises ready-made for you, and you can just skim over those. If you want to do this all step by step yourself, then I would probably assume you want to have 1 to 2 hours, depending a little bit on your previous knowledge and your previous experience, per module. So, for example, in the first one, where we discuss a little bit the structure of the FASRC, that is easily explained, I guess, but really to click on all the websites that we introduce and go there with the terminal, with the command line, use SSH to connect to the cluster, and then start a compute node session. We go into detail about all of this. That can take a little bit of time. So depending on your previous knowledge, I would say you're good if you have around about 2 hours ready. But as I said, whenever you feel like, no, now I want to skip over something, the material is ready for you. So I also introduced or mentioned that there is a GitHub repository. I think right now is a good time to pause this video quickly and go on this, hit this link here. You find it in github.com/CGA-Harvard and then /Python workshop GIS Big Data. In this repository, you find 4 folders, chapter 1 to 4. These are the chapters from the agenda that you just saw. And exactly these slides as well. You find the slide deck for the presence workshop that we gave here on September 26th, as well as the slides that I use here for this video presentation. So you can follow each of these slides individually. And there's not only a PDF version, but also the PowerPoint or Word version of everything. So you can make your own comments and change it as you like. Also, this repository comes with a little cheat sheet. So when preparing for this workshop, I found it myself quite handy to just have a little bit of an overview of all the different commands and all the different tools that we use here. And there's a PDF file with only 3 pages where the most important commands are listed. Now, this file also contains the links to, for example, the datasets. The datasets are open access, so you can just download them yourself, and within the slides, when we discuss it, you will find links to where we got the data from that we work with today. If you want to spare this and just want to follow an easy way to do this yourself, this Google Drive link here will provide you with all the data that we introduce and that we discuss here in the workshop. But as I said, you can also check out the full versions because, of course, this workshop now is made in late September 2023. And we are, for example, working with some social media data, and now this data is updated on a daily basis. So if you want to find out more about the data of 2023, although you are watching this in, for example, January 2024, then it might make sense to look into the original sources of this data set. But to get you started and to get you running as quickly as possible, these 2 links get you covered. Now, without further ado, let's jump right into chapter 1. What is big data? Well, if you read about big data and you Google that, then you mostly very often find mentioning of the 3 V's. These V's stand for volume, velocity, and variety. Now, volume is just the sheer size of the data. As a rule of thumb, I consider myself big data as everything that I don't want to run on my machines, right? So if that may be a laptop or a desktop computer somewhere, or even a small little server, big data is probably everything that's just above what's comfortable to handle with. So for example, here at the Center for Geographic Analysis at Harvard, we have an archive called the the GeoTweets dataset. And these are all the tweets since 2012 that come with a geographical reference. Now, all in all, that's only 2% of the entire Twitter throughput. But these 2% since 2012, they come with a reference of where these tweets were posted from. They might not be perfectly accurate down to the inch, but they are accurate that we can definitely group them from different regions of the world. And this gives us a great possibility in all sorts of analysis and different fields and research areas to make sense of what do people write, how they write about something, what is important where, and so on. Now, this data set is by far larger than what you could fit on any consumer-grade hard drive. So here, when you process something like that, that's definitely something where you want to have huge resources, such as a high-performance cluster, that you can't manage on a single laptop because your hard drive would just be full and it couldn't cope with all this lot of data. You just couldn't copy it, so you can't process it there. So then you need some strategies for big data. Now, velocity is the speed at which new data is generated and collected. For example, as well in our social media context, with our tweets, I think only with our GeoTweets, we are looking at 150,000 tweets per hour. As I said, only tweets with geographical references. So that is something that easily keeps many computers in a row very, very busy to a degree where they can't be used for anything else at the same time. So this is something where we also have just a hardware need to process something that we couldn't do otherwise on our machines that we usually work with. And then variety refers to the different types of structure, like do we have unstructured data, like pure text, right? Human generated content is most often unstructured, just something that some people post on blogs or in tweets or on different social media websites. These come in all sorts of varieties. Some people write about numbers, some people write about text, and then how to make sense of that and how to process that. Now, other data sets, for example, come as a JSON or a CSV file that is already in a structured format and could be easily interpreted for a computer. But most often, these data are just a mix of all of these. So here we need different analysis strategies of how to handle which kind of data and how to pre and post process those. Now, over time there were two other V's added to this list, veracity and value. Veracity here refers to the reliability of the data. So if I have 100% guaranteed access to my data, 100% is probably a little bit unrealistic, but 99.99, and then you can make contracts to your cloud provider of how many digits after the comma you want to be able to access that. Then we have value, like the usefulness of your data, because if you invest all these resources to really make sense of this data set, and you really want to make sure that it is valuable and is something that you can actually use for the purpose you intend. Now that's roughly big data. I have a few more comments in the slides, so sometimes it makes sense to refer back to the slides, to the PowerPoint file here, because most of these slides come with some more comments that I just don't say now, but if you are more interested into this, then it might make sense to look there. We also, when we talk about big data, we speak about processing, which mostly refers to taking these vast amount of data in these all different forms of structure and then really get these information out of that we actually want to work with and only store these, right? So mostly if we are, for example, in a pandemic situation, interested in numbers of an outbreak or of how something develops over time, then we are, for example, more interested in how many infections do we have in an area per day, and not in all these raw data that really reports these numbers in the first place. So it might make sense to first process that a little bit and then save and store only these information that we think we would need in a later time, which of course is a trade-off, because then if we do that, then we can't later come up with a different research question that our data set now won't enable us to pursue here. But this is something that we also need to consider. Lastly, if you are here and you're watching this course, then you probably stumbled across that already. I just briefly want to mention what FASRC stands for. That's the Faculty of Arts and Science Research Cluster, basically Harvard's High Performance Computing Cluster. That being said, there is a differentiation to be made between cloud providers and a high-performance cluster, just in general. This, for example, is also a slide where it might make sense to go more into detail, because there's a whole host of information written down there. Here, I just want to briefly go into this fundamental concept that a cloud provider in general wants to create an environment and an infrastructure where then clients can rent different pieces of equipment and hardware or infrastructure to host a service on their own, and then be able to scale. So scaling is probably the most important part for many cloud providers, because they sell fundamentally the ability of, yes, this is your infrastructure, but now if you have, for example, an online shop, and this online shop before Christmas, for example, just experiences a peak in the load and the usage, then this customer pretty surely wants to ramp up their resources they have dynamically towards the load that they experience at any given point in time. So this is what Microsoft Azure or Amazon AWS does. Now, a high-performance cluster wants to scale to problems and to research questions and to tasks, but probably not as dynamically as you have in a cloud infrastructure. So at a high-performance cluster for research, as we have it here, the use case is much more, hey, I developed something on my laptop, but now I reach a performance limit that I can't tackle anymore. Now I need more performance to pursue my research. Now, I have a problem or something that I want to solve in mind already. I want to run this job that encapsulates my process for a certain amount of time, at a certain amount of memory, with a certain amount of CPU cores. But these requirements probably won't change dynamically, like in the first day I need 20 cores, and the next day I need 3 cores, and the third day I need 50 cores. That's unlikely in these research clusters because we know pretty much before we start the job what is going to happen. Like, we know the data, more or less, we know the research question, we can pretty much anticipate what is happening at which given point in time. So from an infrastructure provider's perspective, it's much more important for a high-performance environment to provide infrastructure that is accessible to a large number of users. Here, the FASRC, I think in their documentation, mentioned to be aware that at any given point in time there is roughly about 800 users. Like, these 800 users have potentially some problems that they want to run here that require really huge bandwidth, huge resources. But all of these 800 tasks, like let's say each user would correspond to one task, then pretty much knows what they're going to get into, while as in an infrastructure for a cloud service, variability of resources and dynamic scalability is just a different topic. But there are a few more things that mostly falls into architecture, maybe flexibility here, maybe even purpose. But there are a few more things I cover in the comments to these slides. But basically, just have in mind, while you can probably use a cloud computing environment for your high performance needs. So, for example, if you change the institute and you don't have access to FASRC anymore, then there's a very, very good chance, like almost guaranteed, that you will find a cluster, a cloud provider that will host your scripts and that will enable you to run your scripts there as well. Although the infrastructure is a little bit made for different purposes, right? So, and then of course, the FASRC is free for Harvard users, which is probably the most important benefit here for you, because when you watch this video, I assume that you are a Harvard student or researcher or staff or faculty member and have access to the FASRC, which is then a huge advantage over a cloud provider that, depending on the contracts with your institute and the cloud provider, may not be for free. So it makes absolute sense to go into understanding how the FASRC may work for your purpose. Let's discuss a little bit the structure of the FASRC. Now, this pictogram I found in a YouTube video from the documentation and the FASRC team. There's a link on the side. Check out the entire video. I want to show it here to you because I think it captures the entire structure really well. Basically, you, on your client, always first connect to a so-called login node. That's our first little computer here. It's actually not one, it's multiple, but for the sake of the argument, let's say it's this one single instance that you connect to. Now, from there, you then specify what do you need, what is the resources and the requirements for your tasks now. And then depending on your requirements, you are assigned, you can't choose that freely, like you kind of can, but basically the general use case is you request resources, and given the request that you send into the system, you are assigned a compute node. Now, the compute nodes, this is a bunch of servers equipped for a little bit different purposes, which we get into in a second, that are made for the heavy lifting. That's where you execute your scripts, where high load is to be computed. Now, these compute nodes are to be distinguished from the file storage system. Here, the shared disks. That is where your data is hosted. And these are not necessarily the same systems. So it makes sense to keep this architecture in mind a little bit when you are processing huge numbers of data, because depending on where your data lives, you experience better performance or worse, because they might not be stored really close together. And this makes sense in a system that's as large as this one here is. If you access the FASRC, you have basically two options. One is the web interface. On our command cheat sheet, there's a link to that, also in the exercise. Or you log in via SSH and use the terminal and the command line to connect to that. You will be asked about your username, or the username is what you enter into this SSH command in the first place. Then you are asked your FASRC password, which is not to be confused with your Harvard key. and then a verification code, which is the two-factor authentication number, mostly the 6-digit code that you get from your smartphone or your little widget on your computer for this second factor. One thing that I want you to keep in mind is don't execute heavy load on the login node, right? The login node is a shared resources. There aren't too many of them. And all the people who use the FASRC have to jump through this login node to get to their performance cluster. So if you want to execute something that requires a little bit of power, a little bit of CPU load, then please do that always on a compute node, executing your scripts, maybe creating a different environment, downloading things. Downloading is probably the borderline, that's probably okay on the login node, but it's okay to work with files a little bit, but everything that you really execute where a program is involved that computes something, make sure you do this on a compute node. To go to your, or to jump to your compute nodes, we use slurm. Slurm is a job scheduler and a program that takes care of your needs and what you want from in terms of resources, and then allocates you to a given node in the system or in the entire network that matches your resources. It's also the tool that makes sure that no one exceeds these requests, right? So if I, for example, request 3 CPU cores, but then my program that I actually use is using 8 different processes, then on my usual computer or laptop, the operating system would try to distribute these 8 processes across the different cores. Now, not here, because Slurm makes sure that I only get to use 3 different cores at the same time, and therefore I can't get more performance out of using more processes, which is actually a good pitfall if you're looking into parallelization. That is something to keep in mind. If you wrote a program that, for example, can make use of multiple cores, but you don't see that multiple cores are actually used, make sure that in your Slurm request, when you are requesting your computing performance, you are actually asking for multiple CPUs. Now, there are basically 2 ways to use the system and to ask for computing performance with Slurm. One is the most dominantly used, which is just submitting a job to a queue that will be then asynchronously run. And that basically means you write a little program, like you have your job, what you want to do, then you write a little program like a batch script, and then you tell Slurm, hey, I need this amount of CPU power, this amount of memory, and for probably this amount of time, and here is my script, please execute this once you get there. And as soon as possible, Slurm will allocate a resource in the network for your script there, and will make sure that it will be run. Now, this is great because it's asynchronously, so you submit this job and get a feedback that, okay, that worked, thank you very much. And then it will be done at one point. You can also specify to get an email when it's over, but you won't need to be logged into the system while this is running. We will get into this when we discuss how to move things to the FASRC, but basically Slurm is the instance that takes care of these job requirements. Now, there's a second version that we discuss here. You can run an interactive session indicated by a command called srun for slurm run, then --pty, which asks for please connect me, like you would with SSH, to my compute node so I can interactively walk around and do things there, which is very, very helpful if you're testing something, if you just copied your program and want to see does it really work in the way I intended it to work, and therefore this is really handy. Now, the FASRC comes with different partitions. That's the word that they use for different types of nodes that are available for different jobs. Because for some jobs you want to run, for example, a heavy machine learning application that requires some GPU cards for your model to run on. And this is just a very different hardware system than if you just need something that has a lot of CPU cores, for example, to work with some data sets in Python. Then there are systems which require or which provide a vast amount of memory for your tasks, and then there are other systems which just come up with a little bit more of a traditional version of memory. So depending on the task you want to run and depending on your needs, there are different nodes available to you. These different systems are called partitions. There's one partition which probably is ideal for testing things out in the first place if you're just getting comfortable with the system and if you want to play around with it a little bit, or if you want to see if your job actually runs as expected. That's called the test node you find here in this partition. There is a time limit for all of these machines, well, almost all of these machines. And you see from this table, there is a number of nodes available. So of this test type, we have 16 nodes in the system. They all are equipped with processors that will provide you with 48 cores in total. And in total, they are just shortly above 200 gigabytes of memory. Now keep in mind, these are shared resources. So you request something to Slurm and say like, hey, please give me 32 gigabytes of memory for my task here. And then Slurm will allocate you to a node where this is available. Now, since we have only 16 nodes here of this test unit, it might be possible that if many people are testing their software, it takes Slurm longer to find a spot where they can place your task, especially if you're requiring a lot of resources. Therefore, just make sure that we have this shared partition as well that's coming at 530 different nodes. So we have 530 computers that are equipped with 48 cores and close to 200 gigabytes of memory. This is probably where you'll run most of your tasks, so going with shared mostly makes sense. Probably the only thing to keep in mind is if you use something that requires a GPU, we also have that and can provide that. That's just called the GPU partition here. Of these, we have 15 systems, and they come with 4 V100 cards here. So basically, depending on your job and depending on the resources you acquire, you can choose a different partition for your job to run. There are also possibilities to get individualized and specialized nodes. These are need to be discussed with the FASRC team, but for the general public, the general group of users, these are the available partitions here. Now, storage, I also indicated that storage is a very important topic here. Basically, the most important thing you should, I hope you keep in mind from this presentation here is there are 2 different sites that all together form the entire SAFRC. Now, that is important to keep in mind when you're working with large data sets, because you want to make sure that your data is actually executed or processed on the same side of the network than where your scripts are. Like the scripts and the data should be on the same site. And this then is important where you upload your data into the network or where you download it from the network again. There are a few options to consider, and you can get in touch with the FASRC team to help you. Here is an overview of the entire structure of the network. Basically, the clouds indicate different access points into the network or access points to the internet, and how to access the FASRC. The green nodes depict where network hubs are. Probably not too important for you as data scientists here, but the yellow points, yellow nodes indicate storage elements, and the blue one indicate compute nodes. Now, this is very important because depending on where these elements and these nodes are, they have different network performances. So as, for example, as you see here, most of these outside connections are connected with a 10 gigabit connection to the internet. So for example, if you go to the Holy login node or the Boston login node, if you connect to a login node, then you get assigned to either one of those. Then you know that you are technically linked with probably with a 10 gigabit connection. If you have a 10 gigabit connection in the first place to communicate with the network, to communicate to the network. If you are working on your laptop, are, for example, connected to the edu-roam Wi-Fi, and then use the VPN, then you won't see much more than, for example, 15, 16 megabytes per second of up and download speed here. This is because of the VPN and the Wi-Fi. So if you're working with huge data sets, make sure that they are coming from a link where they can theoretically go into the network really quickly. If you have something that is super large, then you should definitely connect to this Globus site here that has a 100 gigabits per second link. How to do that, please consult the documentation, but now you heard it. And all I'm saying here in this presentation right now is Wi-Fi, probably a bit cumbersome to really take on large data sets. Use, for example, the internet connection to these nodes. The login node is okay to download and upload data from. That's something that you can run there. You don't need to do this via a compute node. So login makes absolute sense here. And as I said, we have the Holyoke site and the Boston side of the entire network. So if your data, for example, is stored on a Boston storage node, and you want to compute something here on this new compute node on the Holyoke side, then you should be aware that you probably go here over this 1 gigabits per second link, which then would explain why you have a lot of latency and not as a good connection into the network and combining your data and your compute script. So instead, what you want to do is, if you want to execute something here, you want to make sure that your data is stored here on the Holy Store or the Scratch sites, because they are then connected with InfiniBand, which is the industry's fastest way to connect two different networks or computer systems with. As I said, downloading, uploading the data into the network is something to consider, and also where's your data stored and where's your data processed is something to keep in mind and to consider. Now, a related question to this is where to store my data if I just want to work with a data set. Where do I put it, right? On your home folder, you generally get 100 gigabytes. That's good for result files, for smaller data sets, for anything that you work with regularly, because it belongs to your account and it just lives there and it stays there. That is a very important thing. However, don't expect high I/O performance, and ideally don't use it for high I/O performance use cases, because the login nodes and your home directory is not designed to handle high throughput there. We do have a local node that is where my task is executed. Like I asked the slurm system, hey, please allocate me to a compute node so I can run some code there. And then it says like, yeah, sure, here is your compute node, have fun. Now this compute node that I'm working on, this comes with some storage depending on the node you are on. That is between 200 and 300 gigabytes. That is great, that is fast, that is quick, that is amazing to use. But two things to keep in mind. One is it's shared with all the other users. So if someone just runs a heavy task that writes gigabytes and gigabytes of data into the storage, that might be problematic. Ideally, that's not you, because this is a shared resource and we should just look out for each other a little bit. What is much better suited for this? My second point, what is problematic or just important to keep in mind here with the login or with the compute nodes storage, the local Scratch. The local Scratch you find as under /Scratch on all these systems. Now this data there, it lives only for the job duration. That means you submit a job to Slurm and say, hey, I need 20 minutes of computing time on a compute node. After these 20 minutes, you have no way to connect to the system again. And if you store some data on the local Scratch of this node, then this data is afterwards lost. So you have to make sure that your script or your job that you're doing, in the end, eventually, copies all the data it creates somewhere else so you are able to access that. Otherwise, it's just gone and did nothing because you can't really access that anymore. There is a global Scratch. A global Scratch is basically the same concept, a shared storage that all the users of the FASRC use with each other. This is super large. That is comes at a space of 2.4 petabytes. That's 2,400 terabytes, which is shared across all the users of the system. And data there lives for 90 days. That is very important to keep in mind. So you have about 3 months to store something there and then to retrieve it. And it's perfectly fine and exactly intended for use like you compute something, you generate a new data set, you store it there. And then you have to make sure that after this, your job is done, you retrieve your data there and then process it further, copy it somewhere else, or download it, or do whatever you want with that. However, it's important to keep in mind that it will be lost after 90 days if you don't do that. Now, that's not necessarily a huge problem, because data that lives there is generally downloaded somewhere in the first place or generated with some scripts or with some tools on the cluster. So therefore, it can be retrieved. It's just a little bit annoying if you wait for 10 days for your data set to arrive or to generate, and then it's lost because at one point you forgot to copy that. So keep in mind, there are these three most important classes of where to store something. Your home folder is great. It's accessible everywhere. That's probably a very important point to make here. The network storage is transparent. So on every system you are, the login nodes, the compute nodes, wherever you are, you will find the same data structure. You SSH to the login node, for example. You type ls and you see your home folder. And all the data that's there is just available for you to use. Now, you ask Slurm to get into an interactive session on a compute node. You type ls, you are in your home folder, you see all the data. So this is fully transparent to you, and you as a user of the system don't have to keep track of on which machine and which machine ID was my data actually stored. Instead, you see all the data available at any time, and you always have /scratch and /n/scratch. /scratch is the local scratch of the machine that you're on currently, and /n/scratch is the global scratch, the thing within 90 days. So just keep in mind, where you put your data is important, mostly in terms of how does it get there, how does it move on from there, where does it live, does it belong to you, like is it yours and won't be deleted or touched, or is it temporarily there, like on the scratches that lives on /scratch only for the time of your job, or on /n/scratch only for the time for about 90 days. All this information you find on this table as well. All these tables that look like the same here, they are from YouTube videos from the FASRC team, and the link and the source of these images is always next to the slide. So if you want to learn more and want to understand what the FASRC team has to say about that, please make sure you check out these videos. As I said, I mentioned it a little bit already, there is a code of conduct how to use such a system, because we are not the only ones using it. There are many nodes for sure, but there are also many users using it at the same time. Expect more than 800 users using it at the same time, so you're never alone on the system. And what you do just might influence other people. So it makes sense to watch out a little bit for each other to ensure that everyone has a good experience using the system, and request only the resources that you need. That means, ideally, don't request 100 slurm jobs at the same time that only run for a few seconds, but maybe try to engineer your scripts or your tasks in such a way that one node can then run multiple tasks, maybe in a row or like in a chain. The documentation also hints at Slurm coming with a certain amount of overhead. So whenever you submit a job there, this creates a lot of overhead, things to consider for the program in order to manage everything it has to do. And therefore they are asking, please don't request a Slurm job that's running less than 10 minutes. 10 minutes should be the minimum here, and the maximum depends a little bit on the partition that you submit your job to. So for example, at the test partition, I think it's 8 hours or 3 days. It's on the table. Also, login nodes are not for jobs, but are not for heavy lifting, for actual compute power, but only to submit jobs and to organize your files. And also make sure that where your data is stored makes sense for you and for others, so you don't accidentally write the entire scratch or fill up the entire scratch on a compute node, because others might use that as well. Now we have an exercise, as I said in the introduction. I just briefly go over the exercises, then you'll find a file on the GitHub repository that explains all of this in more detail and gives you a step-by-step description of what to do. So please make sure to first log into the FASRC web interface. There's a URL for that, and just start an interactive Jupyter Notebook session. The default settings for now are okay. The default settings give you 1 core, I think 4 gigabytes of memory, and it runs for 2 hours, I think. You can double check that, but that's for okay to play around with this for now. In this Jupyter session, like it takes a second, it says like job is queued, then job is starting, and then the job is running, and then you can connect to Jupyter, all in this neat web interface. Now in the Jupyter interface, this is now running on a compute node. So that is actually your first interaction with the computing performance node of the cluster, and everything you run there in this Jupyter session then runs on an actual compute node in the system. This is cool for two things, or you can do two things now. One is just create a new Jupyter notebook, and I would say go with a classic example, something really simple. I just want you to get the feeling of, hey, I programmed something and it does something, and this actually runs on the FASRC, yay. So just go with a simple hello world, for example. Create a new Jupyter notebook file, type that in, run, see if it works. And if it works, then you know these lines of code, hello world there, they were generated on the compute node of the cluster. What you also can do in the first start page of the Jupyter project there is a little file. You can create other files, like all the files you want, and edit them. You can't run them if they are not notebooks in the web interface, but that's okay. You also find a little terminal icon there, and if you click that, then you are in your browser. You started a terminal session on this compute node. You can move around there with your usual CLI commands and have a look, or generate new SSH keys, or download some data, or whatever you want to do, which you can then later use in the Jupyter Notebook project as well. Now, second, let's try exactly the same, but now use the terminal and log into the login node using the terminal and SSH. There's a key, or there's the path where you go. Here at user@login. Make sure you replace the user with your actual FASRC username, not your Harvard key, but your FASRC username. And then create a new Python environment. In the GitHub repository, I prepared a requirements.txt file for you. And this file contains all the packages that you most likely will use during or when you work through this workshop here. And it comes with all the tools that you want to have. Now, here the exercise explains how to create this new Python environment. And after you created this environment, and this will take a few seconds, that's okay, that takes a while. After you created this environment, the Jupyter Notebook website in your browser that you started one slide earlier, this one can then is able to access your new Python environment that you can select on the right-hand side. On the right top side, there's a little Python 3, I think it's labeled. And if you click there, you can select different Python environments. And after you created the environment that comes from that supports all the libraries and all the packages that I prepared for you in our requirements.txt file, then you will be able to select this environment as well, and you can just work in the Jupyter project or on the command line or your local machine as you wish. Now, of course, if you want to work on your local machine, also make sure you create exactly the same Python environment and use the exact same requirements txt file. And the exercise worksheet provides you with a little command of how to download this requirements file into your folder when you are, for example, in an SSH session. One thing that I didn't mention so far, because the FASRC covers a lot of different use cases and projects that you can possibly do there, it makes sense to group certain tasks and programs and installations for the user, so not everything is available for everything, because that would just increase the time to load everything, and second, probably override and create some conflicts there. So therefore, it comes with a module system that enables you to load different modules. Now, this is not to be confused with Python or environments for different programming languages. These modules are more for the operating system in the background there, and just indicates, hey, system, please load all my Python tools here. Now, I go in this example with the module called MambaForge, because in the FASRC documentation, I read that they prefer Mamba as a packet manager for Python dependencies. There are different modules to use, so I think there's also a Python module there. I go with this, and this is consistent throughout the entire workshop. If you are used to do something else, then it's perfectly fine. Do just what you're used to. Here, I just go with this. So first, I'm on a new node. Doesn't matter on which mode. I always first load the Mamba environment that gives me access to all Python, to Mamba, to Conda, to every tool I need to really work with Python then. And then second, I create, or after I created it already, I just load this environment here with Mamba create, or probably what you're more used to is Conda create and Conda activate. Mamba is actually just a wrapper for Conda commands here. After you've done that, start an interactive session on a compute node. That's the same command that we saw already earlier in the slides with srun --pty. That gives you or puts you into a compute node right away. Here again, it's a new computer, it's a new system, so we again load the module that we need to work with Python, and then we activate this, and then we just run code. I've also included a little tool for you to convert a Jupyter Notebook file to a plain Python file. After you've done that, you can just execute that as you are used to this, Python, and then the file name of my little code here. And then you should see hello world. So all the best with that. Here you find all the slides. That's a link to the GitHub repository that should you get you started, and all the files you need are also in folder 1. Now, what have we learned here? Well, the FASRC comes with a web interface and a command line interface. The FASRC is available through both of them. We discussed how to get into a terminal, even through the browser, or of course via the command line. The command line is the main access channel, but sometimes it makes sense to have just a backup plan to get there. Slurm is a manager for resources, and you always request something first, and then Slurm tries to allocate you somewhere on the compute node that you can that fulfills your needs and your requirements. And the resources must be known beforehand. So keep that in mind. If you ask Slurm to have a session for 2 hours, but you actually need 2.5 hours, it will just kill your process after 2 hours. And therefore, make sure you require enough resources. But we also discussed that you're not alone on the system, so make sure to be realistic in this case. But I hope you figure it out and get some experience yourself firsthand with the exercises, and all the best with that. That was chapter 1 of the course. I hope to see you soon in chapter 2. Enjoy!